Our research group focuses on developing and applying advanced electron microscopy methods for microstructural characterization and in particular defect analysis in materials of interest for a variety of technological applications. There are two major areas of electron microscopy: transmission electron microscopy and scain electron microscopy. And TEM is very powerful for looking at defects. However, it requires a lot of destructive sample preparation, whereas SEM does not. So what our research tries to do is figure out all the different ways of doing TEM, but doing it in the scain electron microscope so you can look at defects over large areas of materials, spanning millimeters in size even, and doing it non-destructively. First project is by my PhD student Matthew HECHT in material science and engineering, and he's utilizing electron microscopy to look at carbide particles in ultra-high carbon steels. These are a class of steels that are very hard, very robust for forming and shaping of other softer metals, including other steels. Carbide particles are a critical component of the microstructure in these steels, and he's utilizing statistical analysis of hundreds of micrographs to look at particle size and evolution as a function of different processing / heat treatment conditions, and relate those effects to the mechanical properties of the steel. Prince SINGH is a mechanical engineering PhD student. He's utilizing automated crystallographic orientation mapping in the transmission electron microscope to look at nanocrystalline materials, particularly thermally stabilized alloys, and the effects of radiation and heat on their stability, particularly looking at grain boundaries and defect dynamics as it pertains to grain growth and evolution. Another student, Anna WEISS, she's a PhD student in material science and engineering. She's utilizing automated crystallographic mapping both in the TEM as well as SEM, looking at nanoscale oxides dispersed in steels. These tiny particles help stabilize the microstructure. They capture defects under deformation conditions, and so we're trying to figure out a way to disperse the nanoscale oxides better in the steel, as well as look at exactly how they strengthen the steel directly by microscopy. Another student is a PhD student in material science and engineering, is Yoosuf TESSERMAN. He's utilizing a Mira 3 manufactured by TESSERMAN to look at electron channeling contrast imaging of defects in a variety of semiconducting materials to do defect property correlations. He's also developing a method to do quantitative strain mapping utilizing selected area mode channeling. And then finally, my postdoc, Marzia Moradi, is utilizing electron backscatter diffraction as well as energy dispersive spectroscopy and fractography to look at the bond strength mechanisms induced by electrically assisted roll bonding of laminates. So these are metal sheets that are pressed together under electrical current, and the current has interesting effects on the interface microstructure. And so we're utilizing microscopy to see what the interface looks like and how defects play an important role in enhancing the bond strength. So a general theme about all of these research projects is that they utilize advanced electron microscopy methods that are not necessarily widely available, certainly to industry, if not even other universities. So there's a significant amount of training for both students and postdocs in my research group on how to properly and best utilize all these various methods so that they can get after the very difficult materials problems that face a lot of different projects here.